Good morning, Earth scientists. Hey, it is Tuesday. The sun is shining. It's going to be a little bit more like spring. Not going to say it's like spring, a little bit more like spring today. We're going to continue talking about gravity, and then we will get into our heliocentric, geocentric conversations. And then the rest of the week is going to be Kepler with the MCAs will be mixed in there. So it's going to be a little bit goofy, but we'll roll with it. Um, Reminder, page 73 is due on Friday, so that's something that you can be working on as well. We're going to come back and talk about, I can explain how distance and mass affect the force of gravity. So let's spend some time reviewing. We did our weight on different planets. And again, has nothing to do with your weight. It has more to do with if you go on to a more massive planet that has more gravity, how is that going to affect your weight? So we talked about 125, 133 was kind of what we used. So just an example of some different things. Then yesterday we jumped, and we compiled all that data. And again, it's so you can make the connection of how gravity varies on the different places you go in the solar system. So here's a scale model of the solar system. So you can see where we are on Earth. What was your weight and jumping distance when we went to Jupiter? Looking at how massive it is. We talked about 133 as being our magical random weight. I put 133 in here, and if I went to Mercury, 50 pounds, Venus, 120, 22 on the moon, 50 on Mars, 336 on Jupiter, 141 on Saturn, 118 on Uranus. You can kind of see the variation of all the different planets. So then my question is, what happens if we took it a step further and went out to the sun? I would be 3,600 pounds on the sun. But my question is, would you look any different? And the answer is no. We would assume like, oh my gosh, you're 3,000 pounds. You'd be as big as a house. But the idea is we would look no different. Our mass does not change, our weight changes. And mass and weight are different. Weight is just a measurement of how much gravity is pulling, where mass is the amount of stuff that makes you up. So even though we talk about all these different planets and stars and would we be ginormous? Oh my gosh, we would be so. It does not matter. Okay, it does not matter where you go. You would look the same. Your mass would not change. So we're gonna just kind of wrap up our jumping activity from yesterday. Get that wrapped up. Talk about that. Go through some of the answers and save it. We're not turning it in. Save it. All right, I can explain the difference between geocentric and heliocentric models of our solar system. We're then going to just do a little background front-loading information. So using pages 50 to 54, we're going to fill out this note sheet, and the note sheet is attached below. What is a geocentric model of our solar system? What's a heliocentric model of our solar system? What does it look like? Draw it. What's Kepler 1, Kepler 2, Kepler 3? And Mrs. Anderson talked about some of those things yesterday. What's the simplest way that we can bring this together? So we're going to get some work time. We're going to wrap up the gravity lab. We're going to work on the heliocentric, geocentric worksheet, as well as you can be working on your lesson review, page 73, which is due on Friday. Have an amazing day, and I will see you when you get back.